In this video, we're going to tie a few pieces that we've talked about together about the dual nature of light and of matter and our models of atoms, and then lead you to some of the kind of more interesting thought experiments that evolve out of this quantum mechanic picture of atoms and quantum mechanics in general, this idea that everything is quantized. So far what we've done is we've taken the Bohr model of an atom, which has this planetary idea of electrons being at fixed locations away from the nucleus, and we've said, okay, this doesn't actually work for all of our elements. And so scratch the Bohr model, and we developed this quantum model of the atom. And this comes out of the work that we just showed of discovering that light can act as both a particle and as a wave. And that an electron, because its mass is so small, can also act as both a particle and a wave. In fact, we act as particle and waves. We just are too massive to observe it. And so if we think about an atom, which is talking about very, very small particles, and especially electrons, which are even smaller than a proton or neutron and have very little mass, then that wave-like nature of matter becomes extremely important in visualizing what is actually happening and understanding how an atom behaves. And so there are some things when we think about this view, we still know, especially from the gold foil experiment, that there is a small nucleus at the center of each atom that contains all the positive charge that's spaced out by neutrons to help make it more stable. And then around it, we have electrons. And they're not smattered around it like chocolate chips in a cookie, and they're not in orbits around the nucleus as a planet, but they are quantized in their energy levels. Let's do it like that. Um, but they aren't orbiting. They aren't in these fixed pathways around it. And what we find is that if an electron is acting as a particle, but also as a wave, when it is attracted to a nucleus, we can think of it best as a wave. And we can describe it with a wave function. And this leads us to Schrodinger's wave equation, which approximates, well, or which describes the probability of how where an electron is and how fast it's moving within an atom. And we'll talk about this some more when we come together in class. But Schrodinger's wave equation is often simplified and written as this. So you'll see it again later too. And so this idea then is that these electrons are going to behave as waves, and we are going to look at the three-dimensional shape those electron wave functions take. And we'll see that some of them will look like spheres. Some of them will have a node in the middle and they'll look like figure eights. Some will have two nodes in the middle. They'll look like four-leaf clovers. Some will have radial nodes inside it and they'll seem like gobstopper candies. Um, and that what we're going to be looking at are these nodes, are these places where a wave crosses zero. But we have, it's not this two-dimensional wave, it's this three-dimensional picture. And so we'll have these lobes of electron density where you can find the electron, where it's likely to find it, and areas where it's not likely to find it. Kind of like in a wave, it's likely to find our wave here, but not here, or here, but not here. And so when we describe this quantum model of an atom, we often say that there's an electron cloud. And that's as best as we can really visualize this. Is there's this space around the nucleus that it's likely, that it's probable the electron exists. But it doesn't have a fixed orbit, and we can't exactly pinpoint where it's going to be at all times, and we can't predict its path that it's going to take. And so we're going to think about the electrons around the nucleus as just the probability that they exist in a space. And we could say that it's probable that they exist in this space, and it's not probable that they exist in this space. And that's going to give us this picture of the orbitals that electrons can occupy. And it'll help us then develop a system for tracking which orbitals electrons are in and how much energy they have because of that shape of their wave function. And so all of what we're going to do in class, these shapes of orbitals and tracking how much energy electrons actually have within an atom, are really coming out of approximations of a solution for the Schrodinger wave equations and the development of these electron wave functions. And from this, we're going to get information about its angular momentum and its spin and its magnetic data about it. And we're going to build from this in class these quantum numbers N, L, M sub L, and M sub S, which are solutions that come out of the Schrodinger wave equation for any atom. And we'll talk about this in more detail. But this is really how we built up into this quantum model of an atom. And the foundation of what we're going to be looking at is that these electrons are going to be acting as waves around our nucleus. And the best way to describe a whole bunch of waves around a nucleus to us is electron cloud. And so we'll use that term a bit, even though it's pretty vague in and of itself. Now that we've kind of combined these ideas into a simple view of the quantum atom that we'll go into more detail in class, I'd also like to point out some of these interesting things that come along with the quantization of energy and particles acting as both waves and as particles. Now, the first one that's, I think, kind of the most important to this class is the observer effect. And so let's go back to our double slit experiment with electrons. So we have a source of electrons that's emitting them at these two slits, and we see a diffraction pattern. We will observe this diffraction pattern when we just observe collecting data over time with an electron source going. If we design an experiment where we try to detect which slit an electron passes through. So we try to detect it before it hits the photographic paper, and we try to detect what is happening to an individual electron. We see the diffraction pattern disappears. So the act of observing an electron means that we fundamentally change its behavior. There's no way for us to design an experiment that allows us to observe an electron without affecting it. It is so small that any detection technique we have affects that electron too much. And so it then acts as a particle again, and it breaks down that wave behavior, which is fascinating. So this is an effect that we can see if we don't directly look at it and try to detect it. And this is this general problem in science, if you think about it, is like, how can we truly observe things without actually affecting their behavior? I mean, can we? So is there an experiment that can be designed that actually truly shows how something is behaving naturally? Because our methods will inherently interact with it to be able to detect it. And you can talk yourself in circles about that for a while. Backtrack here in your notes. I went a little out of order and I apologize. One of the interesting things about Schrodinger's wave equation too is that it's really based on probability. So what we're doing when we solve for it is trying to calculate the actual probability of finding an electron with a specific amount of energy in a specific location in the atom. And this is tricky to do. And in calculating the Schrodinger's wave equation, we find that we're actually calculating multiple possibilities at once. And this is famously characterized as Schrodinger's cat, the problem of Schrodinger's cat, that if you put a cat in a box and you close it up and you put a method in there of killing the cat. So in this case, the ways of killing the cat vary based on who's telling the story. And this one, you have a lever, like you press a button, so you don't know for sure if it worked, that takes a hammer and cracks open a flask that has a chemical in there that'll create a poisonous gas. Now, at the point of hitting this button outside the box is completely closed. The cat is both alive and dead until you open it and observe it. And so the electron is both a wave and a particle until you open up the box and you actually look at the electron. And then it's one or the other, depending on how you observe it. And in this case, you open the box and either the cat is dead or the cat's still alive. But until you actually open it and observe, it is both, which is super cool. Now, this oftentimes gets mixed up with Heisenberg's uncertainty principle. And what that is actually talking about is the fact that electrons are so small. So going back to that, and we'll talk about this more in class, that if you try to determine the position of an electron, you will not be able to determine its velocity or its direction or its path. You can only observe one or the other because observing one will affect the other because its mass is so small. And so Heisenberg's uncertainty principle demonstrates that we really cannot actually know everything about an atom, about an electron in an atom. And all we can really do is figure out its probability of being in a position or its probability of traveling in a direction when it has particular energy. And so when we talk about atoms and when we talk about understanding how an electron is behaving, we will always be talking about probability. It is likely, like it'll be the probability that it exists in this space 90% of the time, something like that, without there ever being any certainty to it, which is this gray area that is really interesting to operate in science, and this knowledge that we've hit a limitation of our powers of observation. And with that comes a joke. I'll let you absorb this joke for a minute. So then this leads into a couple other things. And for the sake of brevity, if this is super interesting, which I really think it is, that I would encourage you to watch this short video about quantum entanglement. And what occurs with quantum entanglement and what that really means. And this does a good job of simplifying it. I'll also link to a video about quantum mechanics that I think is really fun, which is how do we use this to teleport? And like theoretically, we can use this, the cat is both dead and alive, to teleport things in theory, and kind of also not. But these are fun videos that explore this thought experiment about using our quantum mechanical understanding of our universe to develop a teleportation device. So I'll leave these links at the end of this lecture.